Hi, my dear students. In the previous class, we discussed one of the most important theorem, that is necessary and sufficient condition. Okay. Today I am discussing some examples on analytic function based on that theorem. So now, before we see the some important notes. The first one, modulus of f dash of z whole square is equal to modulus of ux square plus modulus of vx whole square. That can be written as ux square plus vx square. So ux is subscript x. So ux is nothing but dou u by dou x whole square plus dou v by dou x whole square. Okay. So that is differentiation. It can be written as ux into vy minus vx into uy. Okay, so we know that. So ux is dou u by dou x and vx is dou v by dou y. By using CR equation in the place, dou u by dou x into dou v by dou y. So dou v by dou y can be written as dou v by dou y is equal to dou u by dou x. So dou u by dou x into dou u by dou x is dou u by dou x whole square. So dou u by dou x can be written as ux. So ux square. So both are same. So similarly, vx can be written as dou v by dou x and dou uy written as dou u by dou y. So by the CR equation, dou u by dou y is equal to minus dou v by dou x. Okay. So here minus into minus plus. So dou v by dou x into dou v by dou x is equal to dou v by dou x whole square. So that is v by x means dou v by dou x whole square. So that is equal to ux into vy minus vx into uy. Okay. By using Cauchy-Riemann equations, it can be written as dou of u comma v is equal to divided by dou of x comma y. That equation written as ux into vy minus vx into uy. So we know that in BSc first semester. Okay, by partial differentiation. So now one second note is Lagrange's mean value theorem. The function f of x is defined and continuous at a point a comma a plus h. Okay, then the function is differentiable at a point c, that is a plus theta h. Okay, then f dash of c, in the place c is f dash of a plus theta h is equal to f of a plus h minus f of a divided by h. It can be written as in this way. F of a plus h minus f of a is equal to h into f dash of a plus theta into h. Now, one more note. We have omega is equal to f of z is equal to u plus iv. So that is complex variable, where z is a x plus iv. Complex variable in the form of u plus iv and complex number in the form of x plus iy. Okay. So now the above equation, that is f of z, differentiation of this equation is f dash of z is equal to ux plus I into vy. Differentiate partially with respect to x. Okay. So now f of z is nothing but omega. So or we can write in this way, dw upon dz is equal to dou u by dou x plus I into dou v by dou x. I already told that ux is nothing but dou u by dou x. Similarly, dw upon dz is equal to dou by dou x into u plus iv. Okay, take dou by dou x outside, we get u plus iv. So u plus iv is nothing but omega. We have to substitute dw upon dz is equal to dou w upon dou x. So now one more important remarks, that is, if f of z is equal to u plus iv is analytic function, then phi is a harmonic conjugate. If and only if phi is a harmonic conjugate of u is in a domain D, then f of z is equal to u plus iv is an analytic in D. Okay, so here u is an analytic function, means u is a harmonic function, then phi is a harmonic conjugate of u. Similarly, phi is a harmonic function and u is the harmonic conjugate of v, vice versa. Okay, so now if u and v are satisfies the Laplace equation, then f of z is not analytic sometimes. Okay, so now, so one more important note: dou square upon dou x square plus dou square upon dou v square is equal to 4 into dou square upon dou z into dou z bar. This is the important formula we can use in the next example. Okay, so now see the examples based on analytic function. Okay, the first example is if f of z is analytic in an open set S. F of z is analytic. We know that analytic, the definition of analytic, the function is analytic, means the f of z is differentiable at a neighborhood point of a z naught in a domain T. Okay, so it is an open set, is analytic in an open set F. Then f dash of z is equal to 0 for all z belongs to the points z belongs to the open set F. Then show that f of z is constant. Okay, so now the solution of this question is that on f of z, it is complex variable, f of z can be written as in this form u of x comma y plus I into b of x comma y. Okay, so f of z is an analytic. So already told that f of z is analytic. Okay, the differentiation of f of z, f of z differentiation is partially with respect to x. F dash of z is equal to dou u by dou x. Then dou u by dou y is 0. We are differentiating partial with respect to x plus I into dou v by dou x. Then, since f of z is equal to 0, so already given that condition, f of z is equal to 0, so that in the place f dash of z we have to put 0, we get dou u by dou x plus I into dou v by dou x. Then comparing real and imaginary, means equating real and imaginary parts. 0 can be written as 0 plus I into 0. Okay, so dou u by dou x is equal to 0. By equating real and imaginary parts, we get dou u by dou x is 0 and dou v by dou x is equal to 0. Okay, now using CR equations, we have to show that the function u is free form x and y. Okay, so the first condition dou u by dou x is 0. Then we have to show that dou u by dou y is also 0. So here, by using CR equation, dou v by dou x is equal to minus dou u by dou y. Then we know that the value of dou v by dou x, put this value, dou v by dou y is 0, then dou u by dou y is also 0. Therefore, dou u by dou x is equal to 0 and dou u by dou y is also 0. Therefore, the real part u and u of x comma y is independent of x and y. The real part u is independent of x and y. Hence, u of x comma y is constant. Okay, so similarly, we have to show that the imaginary part is also a free form x and y. So now, so here we know that already dou v by dou x differentiation is 0. So taken as it is. Then by using CR equation, dou u by dou x can be written as dou v by dou y. Then put the value of dou u by dou x in the place 0. We get dou v by dou y is also 0. Therefore, dou v by dou x is 0 and dou v by dou y is 0. Therefore, v is independent of x and y. Hence, v of x y is constant. Okay, now the both the terms u of x comma y and v of x comma y are a free-form x and y. Therefore, the function f of z is constant. Okay, I hope all of you understood. So now see the one more example. Okay, the second example, if f of z is analytic function such that f of z is always real, then show that f of z is constant. First we understand the question. The given conditions are, if f of z is analytic, we know that what is analytic, such that f of z is always a real, f of z is always a real, then show that f of z is constant. Okay, so already told that in the question, f of z is always real, that means the imaginary part is 0. So now, the solution of this equation, this question is, since f of z is equal to u of x comma y plus I into v of x comma y is analytic. Okay, here f of z is real, that is given condition. That means the imaginary part is 0. Then we have to take v of x comma y is equal to 0. Then differentiation of this function, dou v by dou x is equal to 0 and dou v by dou y is equal to 0. Differentiate the imaginary part with respect to x and y partially. So now, by using CR equation, dou u by dou x can be written as dou v by dou y, and also dou u by dou y is equal to minus dou v by dou x. We know that the values of dou v by dou x and dou v by dou y, subject to these values, we get dou u by dou x is 0 and also dou u by dou y is 0. So now the function u is independent of x and y. Therefore, u is a constant. The real part is constant. Therefore, hence f of z is a real. Okay. So now, in the same way, we have to solve the next example. Prove that analytic function with constant imaginary part is constant. In this question, the given conditions here, we know that the function f of z can be written as u of x comma y plus I into v of x comma y. Here told that the imaginary part means v of x comma y is a constant. We have to take constant value. Okay. Solution. Since f of z is equal to u of x comma y plus I into v of x comma y is analytic. Okay. So now imaginary part is constant. Already told that. Therefore, v of x comma y is equal to constant, that is k. So now differentiation of this function with respect to x and y partially, we get dou v by dou x is equal to 0 because k is a constant. Then differentiate partially with respect to y means dou v by dou y is equal to 0. Okay. Now by using CR equations, we get dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. Okay, by using CR equations, we know that all of you. So here substitute the values in the place dou v by dou y and dou v by dou x. Then we get dou u by dou x is equal to 0 and dou u by dou y is equal to 0. Therefore, the real part u is independent of x and y, hence u is a constant. And therefore, u and v are a constant. Hence, the function f of z is a constant. Okay. Thank you.